Hi everyone, this presentation will be on the relationship between music and mathematics. So the rationale for choosing this topic is manifold. Firstly, it's a widely researched topic. Secondly, math and music are inherently related, and we're going to explore a little bit about how. And this topic is also personally relevant to me as I'm a teacher of math, but also a former student of music. I studied piano and viola for about 10 years each, so this is particularly interesting to me to investigate. So the research questions I have is, in what ways are music and math related? And also, how can musical instruction enhance the teaching of mathematical concepts? So we're going to explore these in two parts. Firstly, how are math and music related? So, firstly, musical theory is inherently related to the teaching of fractions. When we look at a piece of music, that music is subdivided into measures, and the most standard grouping is 4 beats to the measure. So if we take a look at this image is a teacher's connection between mathematical fractions as well as music theory. This comes from a 3rd grade teacher who knew that her students were studying fractions in math class and wanted to make an explicit connection between the math they're learning in class with the music they were learning in her class. So here the whole note looks a little bit like this, and it takes up 4 beats. So it takes up the whole paper plate. Now a half note looks like this, and it takes up half the paper plate. So again, we're making the connection between the musical theory and the mathematical terminology of what a fraction really represents. A quarter note, as the name implies, takes up 1/4 of the measure, and the 8th note takes up 1/8, which is right over here. So 2 eighth notes make up 1/4, right? So now we have basically the addition of fractions represented visually and also musically. Another mathematical property that shows up in music is the property of symmetry. Symmetry is a property in which one image can be moved, flipped, or rotated to match another image. So if you take a look down here at the letter A, okay, this piece of the A could be flipped on top of the right piece, and there would be no overlap at all. It would match perfectly. So that's what we're talking about when we discuss symmetry. Other types of symmetry do exist, such as rotational symmetry. And all of these can be understood as transformations, right? One type of transformation is a translation, which is a shift up or down, right or left. And it doesn't change the shape, it just relocates it. A reflection would be over a line of symmetry. So here we have a reflection over this vertical line. Here we have a reflection over this horizontal line. And last but not least, we can have rotational symmetry where perhaps this A and an upside down A could be mapped onto one another by rotating 180 degrees. Transformations shows up in geometry when we have shapes on the coordinate plane. It also shows up in algebra when we move functions around the coordinate plane. Symmetry shows up a lot in geometry. But again, symmetry can be understood as a series of transformations. So how do these things show up in music? Well, let's take a look at Ode to Joy. If you look at Ode to Joy, there's this little box right around this piece of the music. And in particular, this piece right here, it's got the letters, we've got the notes E, F, G, G, F, E. You can look visually, they rise and they fall in perfect mirror images of one another. So here we have an example of a line of symmetry, right? This is a musical reflection. But that's not all we have. In fact, if we look a little bit further, we can see that in this measure, okay, we've got E, E, F, G, okay? So we notice that each of these notes is separated by at most 1 step difference, okay? So there's a 0 step here, up 1, up 1. And then if you come over here, we're going to scoot back, you can see the exact same thing. Okay, we've got a 0 step, no change, and then up 1 and up 1 again. So this pattern repeats right here, except for it's shifted down 2 units. So you can think of this like a translation down. Okay, so just to show you what you're hearing, I'm going to play just a little piece of Ode to Joy, and I want you to listen for that translation down 2 units. Okay, so that's going to be between the first and the third measure. And I also want you to listen for that reflection, which would happen right here. 1, 2, 3, 3, 2, 1. Okay, and I'm going to play it and I'll move my finger, I'll move the cursor, okay, as you listen. And I'm going to pause it right there. Okay, continuing on. One other way that math and music are related is the importance of patterns. Patterns underlie math and music both. In math, we often consider this a part of inductive reasoning. And in inductive reasoning, we look for patterns, we try to identify what is the rule of that pattern, and we make predictions based on those patterns. It's often how new information is gathered, and then later we can use deductive proofs to explain why those patterns exist. And in music, we notice that there are patterns everywhere. And in this TED Talk, we're going to look for a piece of music that doesn't have any patterns at all. And this underscores, no pun intended, the prevalence of patterns in music. So we're only going to watch about a minute of this, and I do encourage you to watch the rest of it because it's fascinating. But I hope you enjoy the little segment that I'm going to show you.
So what makes a piece of music beautiful? Well, most musicologists would argue that repetition is a key aspect of beauty. The idea that we take a melody, a motif, a musical idea, we repeat it, we set up the expectation for repetition, and then we either realize it or we break the repetition. And that's a key component of beauty. So if repetition and patterns are key to beauty, then what would the absence of patterns sound like if we wrote a piece of music that had no repetition whatsoever in it? That's actually an interesting mathematical question. Is it possible to write a piece of music that has no repetition whatsoever? It's not random. Random is easy. Repetition-free, it turns out, is extremely difficult. And the only reason that we can actually do it is because of a man who was hunting for submarines. It turns out a guy who was trying to develop the world's perfect sonar ping solved the problem of writing pattern-free music. And that's what the topic of the talk is today.
So I really like this because it's an example in which the answer to a musical question came from a mathematical problem, and people were able to extrapolate an underlying relationship between a pattern in mathematics and apply it to music. So there is an inherent structure to both that can be reduced to a pattern. And all of these relationships are going to help us understand why researchers have been so interested in studying the connection between math and music. So that leads us into part 2. What does the research indicate? So the overarching question of this segment of the presentation is, how can musical instruction enhance the teaching of mathematical concepts? We're going to break this down into parts, specifically thinking about listening to music, playing music, and incorporating music into math instruction. Okay, so take a moment to pause the video and make some predictions about what you think. And when you're ready, you can click play and continue. So, music and overall academic achievement. Students who study music demonstrate greater academic achievement than students who do not. And that's been cited in many studies. There are an overlap of math and science concepts for sure. And we discussed some of those mathematical concepts that relate to music earlier. Of course, the science describes how the sound can be produced. But there's a really important distinction between correlation and causation. So a lot of these studies, which are linking academic achievement and students studying music, are correlative. Okay, so they're not actually conducting a study, they're just linking two variables. And unfortunately, without a real study, we can't necessarily say that the music is the thing causing the change. So if we remove variables including demographics, prior academic achievement, the duration of musical study, and attitudes toward school, suddenly the link disappears. So it seems like there might be third variables at play that are explaining this pattern a lot better than just the study of music. One of those things is economic status. So thinking about students who can afford to take lessons probably are going to have a lot more access to the resources that are going to help them do well in school. So maybe it's not the studying of the music that's helping them do school. Maybe it's the fact that they come from a more privileged environment. So let's look at math and music evidence in favor. So Graziano, Peterson, and Shaw in 1999 conducted a study with 237 second graders. And they did this with a population from a low socioeconomic environment. And that's important, as we just discussed, because financial well-being might be one of the things that explains this link. So at least this study is conducted in an environment where generally money isn't a huge privilege, and it's not distributed in masses. So students were divided into three groups. One group received math video game training as well as piano keyboard training. A second group received math video game training and English language training, and a third group received no special training at all. So a comprehensive set of pre and post tests were used to measure proportional and spatial reasoning. Group 1, the one including the piano keyboard training, outperformed group 2, and both of these outperformed the control group. So the main idea of this study was that it provided evidence that the addition of musical instruction does improve mathematical performance. The limitations of this are that it was a quasi-experimental design, so kids were not randomly assigned into one of three groups, and that would have helped provide more evidence that the piano was actually the thing causing the improvement in proportional and spatial reasoning skills. Unfortunately, not all of the studies converge on this finding. So Salah and Gobet in 2017 conducted a study in which there were three experimental groups, one receiving music training, one receiving chess training, and one receiving working memory training. And participants in all categories showed improvement in cognitive processes, but the skills did not transfer among domains. So this study provides evidence that musical instruction enhances cognitive function, but only in the domain where training occurs. So the recommendation is, if you want to be better at something, practice that thing, not necessarily going to transfer. So a meta-analysis, analyzing the research. Fortunately, since there's so much out there, some researchers have looked at all the different studies together and tried to aggregate information and say, okay, what do we do with all this conflicting data? Well, in 2017, a researcher named Bugos found that poorly designed studies tend to show the largest effects. Studies with improved designs show weaker effects, and the studies with the strongest and best designs show the weakest effects of all. So the key takeaway is the better the design, the less impressive the results. So the most common problem they found was that the control group was doing nothing. Well, take a look back here. Our control group was doing nothing in this experiment. Okay, and that can cause two problems. One could be an enthusiasm gap, right? Maybe students are bored and the lack of enthusiasm is causing negative results to ensue. And then there's also a placebo effect. We also have very clear expectations of what we expect, and teachers and students may inadvertently change their behavior based on those implicit expectations. And now we're going to talk a little bit about the Mozart effect. So this is a famous set of two studies which found that college students who listened to Mozart performed better on spatial reasoning tasks than students who did not. So this became really popular, but unfortunately it was a little bit superficial and it could not be replicated. So a couple of the problems were that the cognitive gains lasted only about 10 to 15 minutes. The results of this study were, this pair of studies was not replicable. And last but not least, implications were overgeneralized and then ultimately commercialized. So here we have a study about college students, and suddenly we're playing Mozart for babies. And in fact, it even extended to women who were pregnant with children and playing Mozart to hopefully try to strengthen their neural development. It was quite an extrapolation, and a lot of the subsequent research did not confirm what the Mozart effect even found when they tried to replicate it as it was, never mind generalize it. So what did we find? Well, there are benefits. So although the Mozart effect has been widely debunked, we have found that listening to classical music positively correlates with arousal and mood. So if we think about this a little bit, there's a couple possibilities that arise. Higher arousal could facilitate acquisition of information or performance of a skill. And improved mood might enhance endurance or persistence. So maybe it's the fact that you're continuing to work harder and longer that's creating a better result than the fact that you're smarter or more intelligent. So it could be a habit, not a cognitive process, that's really at work. Finally, let's think about music as a tool for math instruction. So can learning math through music help students absorb and retain mathematical information better? Well, Carolyn Jones in 2018 found that one teacher named Tammy Jorgensen, who's a math teacher from California, saw significant growth on her student standardized assessment scores when she began writing and teaching songs for each algorithm that students were expected to master. Catherine Yoho in 2011 conducted an action study which found that students learned faster and retained longer mathematical information when that content was presented and repeated in music. Interestingly, our memories are stored in the same part of our brain that processes music and emotion. So that makes sense that our students are going to be able to remember mathematical information better because the mathematical information is encoded in music, which is located very closely to the part of our brain where memories are stored. And so music, memory, and emotion are all closely related. Okay, so here's a possibility. Okay, and I'm going to move my cursor up so that way we can read it. It'll take just a moment for that bottom sidebar to disappear. There we go. So the possibility is that music might help students remember individual math facts, and that long-term memory then enables those students to make connections between seemingly discrete topics and ultimately build an integrated system of knowledge. So maybe better memory is helping kids make connections that help them become better math thinkers. So, to do a final debrief of the key takeaways of my research. First of all, math and music have conceptual structural overlap. 3 of those examples are patterns, fractions, and transformations. While this is not an exhaustive list, it hopefully gives you at least a little bit of an idea of how these things are related. Another key takeaway is that learning in one domain, such as music, has not been shown to directly transfer to another domain, such as math. Most studies which report a positive transfer are poorly designed. Last but not least, the use of music as a means of mathematical instruction can enhance acquisition and retention of mathematical procedures. But studying music and listening to music are, at most, indirectly and mildly related to mathematical skills. So here's where I got my image sources, and you'll find a bibliography on a separate sheet. Thanks so much for listening, and I hope you enjoyed this presentation.